Section 8.7, complex numbers, or imaginary. Well, in this section we're going to look at these things called complex numbers, which actually include all the real numbers we've already been dealing with, but also now they're going to include the even roots of negative numbers as well. This is supposed to say even here. So if we recall something like this, we can't square root a number like -4, because 2 squared would give us 4, and -2 squared would also give you +4. So we wouldn't have been able to square root a negative number like this. So we'd say it's undefined, or we'd say it's not a real number. But now we're going to look at these non-real numbers that we call imaginary numbers, or complex numbers. In order to do this, we have to first derive the imaginary unit I. So solving an equation like this, we'll do this. If we have x squared plus 1 equals 0, we could subtract 1 from both sides of the equation to get that x squared equals -1. Okay. So then to find out what x would equal, to kind of cancel out that square, you could square root both sides. If you remember what we've just been looking at, when we have a square root and a square, they essentially cancel each other out over here. And then that leaves us with x equals the square root of -1. Okay. Well, the square root of -1, we don't really have anything to define that, but that's what we're going to call I. And this allows us then to deal with any type of negative square root or any negative number that we're trying to take an even root. So in order to define this imaginary unit I, it is defined as the square root of -1, which would then also mean that if we were to square I, that'd be like squaring the square root of -1 times the square root of -1, and that would give us -1. So to define I is the square root of -1. But then if we square I, it would give us -1. Okay? So what this means is for any positive x value, if we have the square root of -x, we can rewrite it using the product rule as the square root of -1 times the square root of x. And now that allows us to pull this negative part of it out. Because the square root of -1 we're going to call I. And then we can just square root whatever that x value is, now that it's a positive x, using any of our methods we used, where we split up x and to break it down, or if we can actually square root x if it is a perfect square. So let's take a look at how we can do that with some examples here. First example we have is the square root of -100. So we could rewrite this as the square root of -1 times the square root of 100. Okay. Well, we know how to square root -1 now, because we're going to just call that imaginary unit I, and then the square root of 100 is 10. So then we can finish this off by saying that it equals 10i. I is just like a variable. We typically write it on the end. We would write our whole number out front. So it's like we pull out the -1 and then make it a positive 100, and the -1 when we square root becomes I. So -1 times 100 gives us -100, so therefore we can break it up this way. Let's look at the next example. We have the opposite of the square root of -36. Okay, well, handling this, we have the negative out front, but then -36 we want to break up into the square root of -1 times the square root of 36, because -1 times 36 gives us -36. So to square root the -1 portion, well, first of all we have that negative out front. Square rooting the -1 gives us an I, and then square rooting 36 gives us 6. So it's like we have a negative I times 6, which we can rewrite as negative 6I. Okay. So as you see here, these are all considered imaginary numbers. They have that I in them, and using this letter I allows us to square root a negative value. Last one, the negative 8, square root of negative 8, excuse me. Well, we can't square root that directly, but we can break it up now. So let's pull out the negative part of it, the negative 1. And then 8 we can break down into 4 times 2. Because we can't square root 8, but we can square root 4. Okay. So the square root of that negative 1 is going to give us an I portion. The square root of 4 gives us 2. And then the square root of 2, we can't do anything with that. That has to stay under the radical. Okay. So how we would write this is we put the 2I out front and then keep that other square root of 2 underneath. So we would read that 2I square root of 2. Okay. So we'll slide this up now and take a look in a little more detail and see if some other things we've looked at already hold with when we're dealing with complex numbers. So you want to see, does the product rule apply? Okay. So the product rule was that pretty much what we did up here. We had a negative 1 times the square root of negative 1 times the square root of 100 gave us the square root of negative 100, so we could split it up that way. Can we go the opposite direction? If we have a negative square root times another negative square root, could that give us the positive of their product? If because a negative times a negative would give us a positive xy in that case. So is that going to be true? So let's say, using the product rule, let's look at something like the negative square root, or the square root of negative 4 times the square root of negative 9. Okay. Breaking this down using the product rule is we could write this as one single square root and do negative 4 times negative 9 first, and then square root that value. Well, negative 4 times negative 9 gives us a positive 36. Which, if we then square root that 36, would give us a positive 6. Okay. Now, using the definition of I, does it work the same? We have a square root of negative 4 times the square root of negative 9. Let's work this problem out again, now using the definition of I. So, the square root of negative 4, well, the square root of 4 is 2, so the square root of negative 4 is going to give us 2I, times the square root of 9 is 3, so the square root of negative 9 is going to be 3I, and then multiplying these, 3I times 2I is going to give us 6I squared. Okay? Just like any variable, like x times x would give you x squared, I times I would give you I squared. But if we go back to the definition of I squared, when you square I, would get you to be a negative 1. Because if I is the square root of negative 1, then when you square I, it has to give you negative 1. So anytime you get an I squared, it actually gives us a negative 1. So this would be like taking 6 times I squared would be 6 times negative 1, and that is just going to equal a negative 6. So over here we get a negative 6. On this other side we got a positive 6. So does the product rule apply? Well, no, it does not. We have to make sure to use the definition of I if we have a negative square root. So to answer that question, no. Okay. It does not work, so always use the definition of I for negative square roots. Okay. So let's take a look at this now. We have the square root of negative 3 times the square root of negative 7. Don't make the mistake of saying that will equal the square root of positive 21, because we can't break it down that way. We have to use the definition of I always. So square rooting 3 we can't do, so we can just pull out the negative portion, pull out the I, and then keep it a positive 3 underneath the radical. Same thing with 7. We can't square root 7, nor can we break it down into something that could be square rooted. But we could pull out the I portion of it, and then it would make it a positive 7 under the radical. Okay. So then multiplying these now, we're going to have an I times an I, which is going to give us an I squared. And then square root of 3 times the square root of 7 is going to give us the square root of 21. So you see our answer is not the square root of 21, it's I squared times the square root of 21. And remember, when we do an I squared, that gives us negative 1. So negative 1 times the square root of 21, which is just going to give us the negative square root of 21. So then on the next example, we have the square root of negative 5 times the square root of 10. So we want to handle the negative part first, handle the I part first. So we can't square root 5, and we can't break it down into something that could be square rooted. So we handle the negative by pulling out an I, and then we have a square root of positive 5 times the square root of positive 10. So with this, keep the I out front. Square root of 5 times 10 gives us the square root of 50. But there is a way we can break down the 50. Now there's not an I squared, so there's no negative out front. It's just going to stay I. But 50 we could break down into 25 times 2. Because we can square root that 25. So our expression equals I times 5 times the square root of 2, which is going to equal 5I square roots of 2. Alright, flip to the next page of the 8.7 notes. And now we're going to look at dividing square roots of negative numbers. And we do this before we combine any fractions or cancel out negatives. We once again want to apply the definition of I first. Okay. So square root of 75 we want to break down as the square root of negative 1 times the square root of 75. So again, we can pull the I part of it out, and then it's going to make it a positive 75. Same with the square root of 3, we can pull the I part out, and then we have the square root of positive 3. Okay. Now at this point, our i's are going to end up canceling each other, because we have I over I, just like an x over x would cancel, which is nice. And then 75 over 3, we could try to break down 75 as a square root, because 25 times 3 gives you 75. Okay, so we could break it down that way. Square root of 25 times the square root of 3. 25 times 3 gives you 75. But down below we have a square root of 3 as well. So once again, square roots of 3 will cancel each other out. So we just have the square root of 25. But square root of 25, it's a perfect square. Gives us 5. Okay. I can try the same thing on our next problem. Square root of negative 32. We could break down into I times a positive square root of 32, or square root of positive 32, all over square root of 8. So there's not going to be an I to cancel out the I up top, but here instead we want to look at 32 and 8, and we can think of ways to break those down so that you'd be able to square root. Square root of 32 equals 16 times 2, and 8 equals 4 times 2, and both of those we could square root then. Okay. 4 times 2 gives us 8, 16 times 2 gives us 32. Since we have a square root of 2 both in the numerator and denominator, we cancel those out. And then in the numerator we have I. Square root of 16 gives us times 4. Square root of 4 down below gives us a 2. And then we can reduce the 4 and the 2. 4 divided by 2 gives us 2. So we would write this as 2I. Okay? Just reducing that fraction at the end. Alright, so that's how you want to apply it when you're doing dividing or taking products. Handle the I portion first, then if things cancel out, let them cancel out, and to reduce your fractions. Okay. We can next look at adding and subtracting complex numbers, and this is actually very easy. You just treat the I as a variable, like it's an x, and combine your like terms. So if we had negative 1 plus 8I plus the value 9 minus 3I, you just look at what are your like terms. So you could take the negative 1 and the positive 9, because it's addition and there's no number out front of any of these. We don't have to distribute anything. We can just go ahead, drop the parentheses, and combine these things. So negative 1 plus a 9 is going to equal positive 8. And then 8I minus 3I would just be like 8x minus 3x, and that'd give us 5i. So again, you just treat I like any variable when you're adding and subtracting. One thing to remember though is when you are subtracting two parentheses expressions, if we have subtraction, we have to distribute that subtraction to the following parenthesis. So this would become 7 minus 3I and minus 8 minus 6I. Okay. Which then we can combine our like terms. 7 minus 8 is going to give us a negative 1. And then negative 3I minus 6I will give us a negative 9I. Okay. And then the last thing to look at this page is going to be when we are multiplying complex numbers. Okay? If you have one out front of a parenthesis, we need to distribute it. If you have two parentheses, we would need to FOIL. So let's take a look at these. Distributing the 4I. In this one, we'd have to distribute that into the parentheses just as if it was a 4x. Okay. So 4I times 2 is going to give us 8I. And 4I times 3I is going to give us 12I squared. Okay. But then remember that I squared is going to equal negative 1. So it's actually going to be a negative 12. Okay, so we do have to remember in all of these that I squared gives you a negative 1. So that's going to give us a negative 12. So we'll have negative 12 plus 8I. I guess I didn't mention, we always put the regular number first and then the 8I term second. So the negative 12 we write first. Next example, we have two binomials, so we'd have to FOIL. Okay, distribute the 3 to the 4 and to the negative 2i. Then distribute the 5i to the 4 and to the negative 2i. Okay. So 3 times 4 is going to give us 12. 3 times the negative 2i is going to give us a negative 6i. 5i times 4 is going to give us 20i. 5i times negative 2 is going to give us a negative 10i. 5i times 2i, negative 10i squared. Okay. Well, let's take a look at this. We have 12 minus 6i. The minus 6i plus the 20i, we can combine to be a positive 14i. And then negative 10, remember the I squared, it's just going to become a negative 1. Okay. So subtracting 10 times negative 1 is going to make that a negative 10. So what will happen here is we have 12 plus 14i minus a 10, but 10 times negative 1 is going to make that a negative 10, which will actually turn that into positive 10. So this becomes 12 plus 10 is 22 plus 14i. Okay. And then our last examples, and we're dividing complex numbers. So the idea here is that we can multiply our denominators by the conjugate in order to rationalize. If you remember when we did that in the previous section, 8.6. So in this case, we have 8 plus 9i over 5 plus 2i. We have to cancel out the i's from the denominator. We cannot keep i's in the denominator. So in order to rationalize that, we have to multiply by the conjugate of 5 plus 2i, which, if you remember, would just be 5 minus 2i. Okay. So our original problem, 8 plus 9i over 5 plus 2i. We have to take both the denominator and the numerator and multiply by the conjugate 5 minus 2i. Okay. So we'll be foiling in the numerator and denominator. 8 times 5 gives us 40. 8 times negative 2i gives us negative 16i. 9i times 5 is going to give us a 45i. And then 9i times a negative 2i going to give us a minus 18i squared. Okay. Over 5 times 5 is going to give us 25. 5 times negative 2i will be a negative 10i. 2i times the 5 is going to give us a positive 10i. And then 2i times the negative 2i will give us a negative 4i squared. Okay. So we can combine any I terms, like terms, and also I squareds we can turn into negative 1s. So up top here we're going to have 40, negative 16 plus 45 will give us a positive 29i, minus 18 times a negative 1 there. Okay, again, because I squared equals that negative 1. In our denominator, we have 25. The negative 10 and positive 10, well, those cancel each other out. And then we just have minus 4 times I squared, which again is a negative 1. Okay. How I always remember this is that if it was subtraction, if it's some term with an I squared, it just is going to make this become addition here and get rid of the I squared. So again, down below here where it was minus 4i squared, it's going to become just plus 4. Okay, it just changes the sign, or the operation, from either addition to subtraction or from subtraction to addition. So we have 40 plus 29i. This becomes plus 18 now. The denominator becomes 25. Instead of minus 4, becomes plus 4. Okay. Combining one more time here. 40 plus 18 becomes 58. Plus 29i. Down below, 25 plus 4 gives us 29. Okay, so that could be our answer. However, we can reduce this. Okay, we can try to divide a 29 out of both numbers, and actually both numbers are divisible by 29. So we can rewrite this as 58 divided by 29 plus 29i divided by 29. Okay, any fraction, we can, if it just has a single denominator, we can split it up into the two pieces like that, since there's two terms up top. And it just works out in this one nicely because 58 divided by 29 gives you 2. And then here we can divide out the 29s, and it'll just leave us plus I. Okay. So last kind of quick example here. We have 1 plus I over I. This one's a little bit, I guess, trickier. So I we can think of as the square root of negative 1. So since here technically we have a square root of negative 1, we could multiply it by another square root of negative 1 or another I, and it'll cancel out the i's. Well, it'll make it become a negative 1, and we won't have an I down below anymore. So if we have a problem like this, 1 plus I over I. You don't necessarily have to multiply by a negative I to make the conjugate. You could, but instead we could just really multiply by an I, because that will give us an I squared, and I squared equals negative 1. But also up top we have to multiply by I to keep it consistent. So here we'll be distributing. I times the 1 gives us I, plus I times I gives us an I squared. And down below, I times I gives us I squared. Okay. So these become I plus I squared. Well, I squared equals negative 1. And then I squared down below becomes a negative 1. Okay. So when you divide something by negative 1, really all that does is change your signs. So this is going to make the I, when we divide by negative 1, would become a negative I. And then negative 1, when we divide by negative 1, would become a positive I. Or positive 1. So we could write it like that, or how we normally see it written would be 1 minus I, since we write the real number first and then the imaginary portion second. Okay. So that got rid of the fraction altogether, but also more importantly it got rid of the I part in the denominator. And that is all for section 8.7.